Okay, we're going to do a dive into two specific types of series. The first one is what we are calling the harmonic series. This series is simply the sum of 1 over n from n equals 1 to infinity. So if you think about this, this is like the sum of 1 plus a half plus a third, so forth and so on. The most notable thing that you're going to need to know about the harmonic series is that it diverges. Okay, and it's a really interesting one because the summed, the 1 over n, actually converges as a sequence, but when you add the pieces together, it diverges. So it's going to converge to 0, which means that it's like inconclusive with the divergence test. So we actually have to prove this thing diverges a different way. So the first thing to do is to let this thing equal L. Okay, so this means that L is 1 plus a half plus a third plus a fourth plus a fifth, and we're going to get a bunch of these, plus a sixth plus a seventh and plus an eighth, and so forth and so on. So if this thing equals L, right, then L, we're going to make this assumption that L is some finite number that is equal to all of this. Okay, so let's assume that this thing actually converges. Let's assume that maybe if I add this all up, I get some number, and we're going to say that that number is L. Now, I made this list all the way out to 1/8, and I did that for a reason. Because we're going to say that this, in and of itself, is going to be greater than something. Okay, so I'm going to leave the 1 in there, and I'm going to leave the half in there, but I'm going to change the third to a fourth. Now, a third is greater than a fourth, so this is already going to be greater than this, or equal to, right? Greater than or equal to. I'm going to change the fifth, and we're going to change that into a sixth. So making it even more so. And then we're going to change the seventh into an eighth, and a seventh is greater than an eighth. So my claim that this is greater than or equal to still seems to hold. Okay. So if you think about what just happened here, I still have the 1, I have a half. A quarter and a quarter is a half. A sixth and a sixth is 2/6, so that's a third. An eighth and an eighth is a fourth, and then so forth and so on. Okay, so that's interesting. Well, switch the first half with the 1, right? So this gives me a half plus 1 plus a half plus a third plus a fourth plus, well, see, this part, though, is again the harmonic series. That's kind of weird, because this is saying then that the harmonic series sums up to something that's equal to 1/2 plus the harmonic series. So the harmonic series is greater than or equal to 1/2 plus the harmonic series. Well, if these are all positive numbers, L has to be positive. And if I add a half to a positive number, there is no way that L is greater than or equal to 1/2 plus L. So this is a contradiction. This is a contradiction based on the premise that the series is convergent. So if the series is convergent leads me to a mathematical contradiction, this implies that the harmonic series is in fact divergent. Okay, so if I keep adding up these numbers, I keep getting closer and closer to infinity, but I'm never going to actually reach infinity because I can't get there from here. So this is kind of an important deal. So let's not gloss over something that's happened here. The harmonic sequence okay, so the sequence when an is equal to 1 over n, the limit of that exists. The limit as n approaches infinity of an is 0. So that converges. Okay. The harmonic series, which is the sum of the an when this is equal to the sum of 1 over n, this thing does not converge. It, in fact, diverges. So this is different. We got to keep in mind that the harmonic sequence converges, the harmonic series will diverge. This is a really useful series as we get into convergence testing later on. Okay, so the second type of series that we're going to work with here is what's called a geometric series. And the geometric series is slightly more complex. I have two numbers, a and r, and these are real numbers. And a geometric series is a series that starts with that number a and then multiplies it by r to the n minus 1. Okay, so if you think about this in the first term, you just get a. In the second term, you get ar. In the third term, you get ar squared, so forth and so on. Now the question that we should be asking is, does this converge? And the answer is sometimes. Okay, so this will converge when the absolute value of r is less than 1. And not only that, but it's actually going to converge to a over 1 minus r. So not only do we know that it converges, but we know, given a and r, what specifically it's going to converge to. Now, otherwise, it diverges. So if the absolute value of r is greater than or equal to 1, we get divergence. So it is all imperative on this letter r, what its value is, to determine whether or not the geometric series will in fact converge or diverge. Alright, so let's take a look at what this comes out as. Okay, so how do we prove what we just said? Well, we have to examine the partial sums. So we're going to let the partial sum be n equals 1 to k of a times r to the n minus 1. So as we said before, that's a plus ar squared out to ar to the k minus 1. Okay, so now we're going to do something interesting here. We're going to actually look at what is r times the partial sum. If I take r times the partial sum, well, that's going to give me ar plus ar squared plus ar cubed, out to ar to the k. Alright, so now here's where things get interesting. We're actually going to subtract these. We're going to take s sub k minus r times s sub k. Well, if I look at what's going on here, if I subtract the bottom one from the top one, then the ar's cancel, the ar squareds cancel, the ar cubes are going to cancel, the ar k minus 1s are going to cancel, and I'm going to be left with a minus a times r to the k. Okay, so a little bit of work on both sides of this equation. If I factor out the s sub k here, I get 1 minus r. Well, that looks interesting. If I factor out the a here, I get 1 minus r to the k. So this means that the partial sum is a times 1 minus r to the k over 1 minus r. And let's see. Well, if the absolute value of r is less than 1, then the limit as k approaches infinity of a times 1 minus r to the k over 1 minus r. Well, let's see, this is going to go to 0. So this goes a times 1 is just a over 1 minus r, which is exactly what we predicted. So we have convergence, and we have it converging to this, specifically a over 1 minus r. So now I have to show the divergence. I have to show that when the absolute value of r is either equal to 1 or greater than 1, I get divergence. Okay, so let's look first at what happens if the absolute value of r is greater than 1, right? Well, that's pretty simple, right? Because that means that I have this sum, right? Well, I can just take a look actually at the inside, the limit as n approaches infinity of a times r to the n minus 1. If this thing's bigger than 1, this is itself going to diverge, right? Which clearly means that this limit does not equal 0, which means that this is going to fail by the divergence test. Right? So if I take the exponent of something bigger than 1 and keep taking that exponent bigger and bigger and bigger, I get exponential growth. This thing is going to blow up to something that's nowhere near 0. Gets me the divergence test. If r is equal to 1, right, then the limit as n approaches infinity of a times r to the n minus 1, well, this is just 1 to some power times a. It's just going to be a. And a is clearly not 0. So this also fails by the divergence test. So our geometric series is going to diverge when the absolute value of r is greater than or equal to 1. All right, it will only converge when our absolute value of r is less than 1. And when the absolute value of r is less than 1, it converges to a over 1 minus r. So let's do some examples here. Okay, so when you're trying to find a value for a series, almost always on the BC exam, it will be a geometric series. So like they may give you a series like 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 and ask, what does this add up to if this keeps going infinitely, right? That's 40 over 7. There we go. I don't know. Let's try to fix that. 40 over 27. There we go. Okay, so let's try to write this in series form. So I have a sum. I'm starting with 5. What did I have to multiply 5 by to get this? Well, I had to multiply it by something negative. 5 times 2 is 10 over 3, right? Let's see, if I keep multiplying by 2/3, does this keep working? 10 times 2 is 20, times 3 is 9, yep, 20 times 2 is 40, times 3 is 27. That'll work to the n minus 1. Because in the first term, I want to multiply this by 1, so I just get 5, right? So I think this series represents this. Since the absolute value of negative 2/3 is clearly less than 1, this converges, and in fact it converges to 5 over 1 minus negative 2/3. So that's the same as 5 over, let's see, that's 3/3 plus 2/3 is 5/3, which means I have 5 times 3/5, which means this thing just converges to 3. So if you keep adding up these numbers infinitely, it's going to get closer and closer and closer to 3. That's almost seems like amazing and shocking. Let's look at another one of these. Okay, so let's say the problem says I want to find the series of 2 to the 2n times 3 to the 1 minus n. Now that looks really awful, but if you start looking at this in the right lens, you're going to see that this is a geometric series. We're going to leave the 2 to the 2 out alone for a minute. And we're going to reshape this by taking negative n minus 1. Aha! There's where the n minus 1 is going to come in. So something to the nth, or the negative power, this is just 1/3 to the n minus 1. So that was hiding in there. Sorry. All right, so, but we still have this exponent up front. Let's move this around a little bit. 2 squared is 4, so that's 4 to the n. 1/3 to the n minus 1. But I have an n here, right? So let's pull a 4 out. 4 times 4 to the n minus 1 times 1/3 to the n minus 1. Seems to work. So this is going to give me 4 times 4/3 to the n minus 1. And there we have it. It is, in fact, a geometric series. But the absolute value of 4/3 is greater than 1. So what does this tell us? This tells us that this series diverges. So the series diverges. It's not going to go to a limit. And that's the game. All right, so recapping. Quick little idea here. The harmonic series diverges, and we've proved it. And the geometric series will converge if the absolute value of r is less than 1, and then it converges to a over 1 minus r. But if the absolute value of r is greater than or equal to 1, then it diverges. So this little corner here is kind of like the uptake from this video. All right, thank you.